Hello, I am Robert Washer, and this is my animation blending and GPU-based animation processing demo. First off, I'd like to go through my keyframe compression algorithm that is in my FBX exporter. Basically, what the keyframe reduction algorithm does, it goes through, calculates by given the percent that you passed in. Say you want to reduce by 25%. It calculates the number of bones you need to reduce the not number of bones, the number of keyframes you need to reduce the animation by. Goes through that many times and calculates the error for each frame and finds the frame with the least amount of error and removes that frame. It calculates the error basically by going through each bone and getting the error for each bone in that given frame. The error for a given bone in a given frame, say the error for frame 2 in this getError function, is basically basically calculate two quaternions. Basically, one is the difference between frame 2 and the one before it, and the second quaternion you're calculating is the one after frame 2, and then the one before frame 2. And you're basically calculating the angle of difference between the one leg and the other, and then that is basically what I am considering the error between the two rotations, between the two bones. I'm not considering translation because for the most part in animation, it's mostly just the rotation that is varying a lot. So that is basically how the keyframe reduction algorithm works. So basically I'm going to go over to where I have the clips and I'm going to convert all the models. Basically it's just going to be converting 3 clips, a run, stop, walk, and 4 clips, and a jump, which is here. And then the base humanoid, one that contains the model, the skeleton, mesh data that it needs. So basically in this bat file, I basically have you converting the humanoid, and it's basically saying it's skinned. I have this toggle that basically removes the translation from the root bone, so that way the lateral translation of the animation is removed, and it's now just in like a stationary position, so that the lateral translation does not mess up any of the blending. And I'll also converting it a second time, but only this time I'm using the keyframe reduction to reduce the number of keyframes in each of the animations. Then I am also converting each of the clips with the toggle, also to remove trans, and also signifying that just to export the animation data. And then I am combining all these pieces into one big rob file called humanoid.rob. So let's run it. So it's going through the first humanoid model. It's wrapping them up. Going to the second humanoid model. As you can see, this one takes a little bit longer because it's going through the keyframe reduction, which takes a decent amount of time to bake out. And now we're done. Now we have this humanoid raw file, which I'll copy over to the engine. Now going over to the engine, I'm going to go basically show you that basically there's this be on GPU toggle, which is basically just a Boolean toggle that's passed in throughout the code, basically on creation, and it's used in the processing a lot, basically to toggle between whether you want these things processed on the CPU or using the GPU processing that I've added. So first off, let's go to set it to where it's processing on the CPU first. And before we actually run it, I'm going to go through basically just kind of the state machine that I created. Basically each of these, all the states basically have these 4 methods which basically control the transitions between states, which is where the blending will occur. So, for example, The jump state, you can't really go anywhere but to a run state from it because it's a running jump animation. So basically the only thing it can go from is to a run state. And the only thing that come to a jump state is a run state as well. But the run state can basically go to any of the animations because it has a decent transition between those. The stop state can go to anything but the jump state, and same with the walk state. It can go to anything but a jump state. And here we have a blend state, which has two states, two child states, a from and a to. Basically, it's going to be blending between the from and the to, given a given delta and how many frames it should last. Basically, in this processing, you basically go in its update. It's calculating its whatever time it's at. It's updating the child states, which could either be blend states or it could also be just a base like animation state, like a walk state or a run state, jump state. But it could also be a blend state as well. It is basically, then it will process that thing if it is in the correct time frame. If not, it's going to exit the blend. So in the process, it basically just, if it's being on the CPU, it just interpolates between the translation and the rotation. I removed the scale from the data just to reduce the data size, as the scale was always 1 anyways. If it's on the GPU, it goes and composes the necessary data it needs for the GPU processing, which we will get to later. For right now, I'm just going to start it up. And here we have multiple humanoids that are doing random different things. So let's go to the first guy here. This guy right now, he's in a walk state, but you can easily transition to other states. Like now he's running, now he's walking, and you can see you can blend. It's blending between different states, and now he's running again, and then to a jump state. And you can slow down these animations, you can pass them up, and they'll all basically keep the same speed given that you passed it. That's throughout all those states. It is a the speed of the playback is controlled by the state machine itself, which is its own class. So that's constant throughout all the animations that are processed. Alright, so now let's go to the next one, which is basically going to be the similar type thing, except this one you can kind of see it's just a wireframe mesh, and you can see the bones underneath it that I have toggled to show. Right here, so now watch him now he's walking. He's going to slow loop down, and then you can watch him blend into a run in slow motion. And for the run, he's going to go into a jump. And he's going to go back into running. Let's have him go back to a walk. And now he's going to stop. Let's have him go back into a walk and speed this up. Alright, now going to the next camera. Basically, these two are basically playing the same animation. The one on the left, the lighter color one, is without any compression. The one on the right is a compressed version of the same animation, both being played at the same speed. So as you can see at the beginning of the clip, there's you can see a big amount of artifacts in how the animation is moving, but the rest of the clip is pretty good as far as what's left. It's just the beginning of the clip has a lot of artifacts from the compression. And then over here we have a movable animatable character. And now he's walking around, and I can have him switch over to a run. Have him jump if you want. And have him come back to a stop. And you can have him start running again, walking, running, jumping to a stop. And that is basically what the animation does as far as blending on the CPU. Alright, so now I'm going to go back, switch this toggle over to GPU processing, and I'm going to actually go through the GPU processing pipeline. So basically, once on the initialization of this GPU animation processor, which is where a lot of the GPU-based logic is contained, it basically creates a whole bunch of buffers that are used to pass data. The first one is basically where all the animation data is stored on the GPU. The second one is the buffer that the animation processing stage outputs to. The next one is where the blend stage outputs to, and then the blend stage reads from the one that the animation processing stage outputs to. It reads from that data and then outputs to this next set of buffers. The next buffer is a buffer that holds hierarchy data, which is basically just telling for a given bone what parent it would end up being, what its parent's index is, so that during the hierarchy stage of the processing, it can find its parent to get its global transformation as for each bone. In the update, it really doesn't do a whole lot in the update. This is the first thing called in the engine's update function. It basically just zeroes out a lot of the data that needs to be reset every update. But in the draw, it basically goes through, it loops through and calls the animation compute shader the number of times equal to the number of animations that need to be processed on a given frame. It then goes through, loops through, and calls the blend compute shader, which is called the number of blends, which is basically the number of objects it needs to process during that frame. So in the given example that we had, it would have typically 5 blends it would need to calculate for the objects that were in the scene. And then it goes through and calls the hierarchy compute, which just cycles over all the results of that output data and updates those values of each bone to convert it from its local transform to its global transform using its parent's transforms. And then I'll go and show you the 3 compute shaders. So basically the compute shader here, it's basically taking the animation data buffer where the animation data is at, has an output buffer, and then it has it's passed in an index and the struct that's interp data, which is basically just give 2 indexes of the frames that you want to process and the value you want to interpolate between the two. It basically goes through, finds the 2 frames you want to interpolate between, it interpolates the value, and stores it in the output buffer at the correct index. And interpolation is just basically slurping the rotation quaternions and doing a linear interpolation of the translation vectors. And then the blend, it's doing a similar process. It has it's now its input buffer, which was what the animation compute was outputting, which is now this compute shader's input buffer. It has a output buffer, which is basically where this one's outputting its data to, and it's passed in an index, and a blend data, which is basically just up to 8 indices to blend between, and the deltas to blend between them for. And it's basically just similar to what the animation compute does. It finds the index of in that output buffer from the animation compute and interpolates between the given indices that are provided in the blend data, and then outputs the value into another buffer. And the hierarchy compute shader basically just takes that buffer and takes the hierarchy data. It basically calculates the given global transform of each buffer, and then outputs it into this output buffer. So it's basically just basically it has a convert to matrix function, which is basically just converting the given data that you have into matrix form, and then it is multiplying out for each one the given global transform for that bone. And this data is basically just what the vertex shader of all the meshes, all the objects are going to use. So like if we go to this base skin one, this is basically we got this buffer of bone mats, which is where that stuff outputs to. And on the CPU side, it's basically just indexing the bones that it wants into that buffer. But on the GPU side, it's just dumping them all there, and it accesses it by the index given. So let's start this up, and I'll show you how it looks when it's being processed via GPU. Alright, so we have all the same characters. So this guy, as you can see, you can still blend between all the animations, slow it down, speed it up, slow it down again, go to a walk, I'm going to go to a run, stop him, start a run, go to a jump, stop him again, and go to the next guy. The only thing that I could not actually get working on the GPU side is the actual exporting of the given bone, updating of the given bone models. So as you can see on the GPU, this one that on the CPU side had the bones showing, I cannot actually show the bones on the GPU. That's the one issue I've run into as far as GPU processing. You can see you can walk, you can run, stop, slow it down, speed it up. Now you see he's going blending into a walk. He's gonna stop. Gonna start running. Add in a jump. Go to a walk. And stop. And you can see these animations here just being processed as they were before, but this time now they're being funneled through on the GPU side instead. And as you can see, it still has the same issue that the compression has because the data is the same. And then we go to this guy, moving guy, and as you can see he can walk around, he can run around, he can jump, and stop, and you can see it's blending between all those animations during his movement. And that is my animation blending and GPU-based animation processing demo. Thank you.